bipolar transistor at room temperature, if the emitter current is doubled, the voltage across its base emitter junction is. So we have to see in a bipolar transistor at room temperature, emitter current is doubled, then what is the effect of base emitter junction? So actually what will be the change in base emitter junction? So IE1, this is the equation for the emitter current, which is equal to I as a reverse saturation current into e raised to minus VBE1 divided by VT. Okay. So this was the first emitter current, and now it is doubled, which is equal to 2IE1. Okay, it is given in the question that the emitter current is doubled. So it is IE2. Let it be IE2. That is equal to IS into e raised to minus VBE2 divided by VT. Okay, and now we will have to find out what is the change in the base emitter voltage. Okay, so therefore that I will divide IE1 and IE2, we will get e raised to minus VBE1 divided by VT whole divided by e raised to minus VBE2 divided by VT. If it is going upwards, we get e raised to minus VBE1 divided by VT plus VBE1 divided by, sorry, this was E2, right? E2 divided by VT. Okay, and IE1 by IE2. What is IE1 by IE2? IE1 divided by 2 IE1. Okay, which is equal to 1 by 2, which is in turn equal to, I am taking the negative outside, we will get VBE1 by VT minus VBE2 divided by VT. Okay. Taking the logarithm on both sides, we will get ln 1 by 2 is equal to VBE1 divided by VT minus VBE2 divided by VT. Okay, and this is minus ln of 2, which is okay, negative and negative cancel out, we will get VT ln 2, which is equal to VBE1 minus VBE2. Okay, which is equal to VT is 26 millivolt, ln 2, we will get 18.02 millivolt. So this is the difference between the two base emitter voltages. Okay, this is the answer, 18.02. okay, millivolt. Okay, now let's move on to the next question. In the circuit shown in the figure, as IB increases the VCE, what happens to VCE? That is being asked here. So I'll write the equations over here. The current over here is IB, this is IC. Okay, right in the mesh equation over this loop, we'll get V minus IB RB minus VBE equal to 0. So this is equation number 1. Right in the mesh equation over here, we will get VCC minus ICRC minus VCE equal to 0. Okay. So VCE equal to VCC minus ICRC. What is IC? IC is equal to beta IB. Okay. So VCE equal to VCC minus beta IB into RC. So in the question it is asked, if IB increases, what happens? This one increases, that means VCE will decrease. Okay, so that is it. The answer is VCE will decrease when IB increases. Okay. Now let's move on to the next question. For the self-biased circuit shown in the above figure, Re equal to 4.7 K, VCC equal to 15 volt, R1 R2 is equal to 15.5 K, and RC equal to 5.7 K. Okay, the stability factor S of the given circuit approximately is. The stability factor is del IC divided by del VBE, where both ICO and beta are kept constant. Okay, also it is given that beta is very larger than 1. Okay, now I am going to draw the Thevenin's equivalent over here. The voltage drop across here, VTH equal to VR2, which is equal to 15 into 15.5 K divided by 15.5 K plus 15.5 K, which is equal to 7.5 volt. Okay, and now what is RTH? RTH is equal to R1 parallel R2, which is equal to, so this is a question, okay, which is equal to 15.5 into 15.5 into 10 raised to 6 divided by 15.5 plus 15.5 into 10 raised to 3, which is equal to 7.75 K. Okay, with that I am going to redraw the circuit, and the circuit will look like this. This is VTH, which is 7.5. Then comes our RTH, which is equal to 7.75 K, and then the rest of it are the same. Okay, plus 15 volt, this is 5.7 K, this is 4.7 K. And now I will write the equation for the loop. Okay, so the loop equation is like this. I write the loop equation over here. We will get 7.5 minus IB into 7.75 K minus VBE minus IE into 4.7, right? 4.7 K equal to 0. Okay, and the equation over here, it is equal to 15 minus IC into 5.7 K minus VCE minus IE into 4.7 K. So our stability factor S equal to, I'll write over here, S equal to a stability factor S is equal to delta IC divided by delta VBE. Okay, so VBE and IC, we have to have an equation where both VBE and IC are there. Okay, so I am going to take this equation. We will get 7.5 minus IB. Instead of IB, I'll write IC divided by beta into 7.75 K minus VBE minus IC is approximately, IE is approximately equal to IC. Okay, minus IC into 4.7 K, which is equal to 0. Okay, now I am going to differentiate this equation. We will get 0 minus 1 by beta into delta IC divided by delta VBE into 7.75 K minus 1 minus delta IC divided by delta VBE into 4.7 K equal to 0. Okay, it is given that, I'll write over here, we will get, I'll rewrite it, we get 1 divided by beta delta IC divided by delta VBE into 7.75K minus 1 minus delta IC divided by delta VBE equal to 0. Okay, beta is very large, so this one will be approximately 0. So what is left here is, okay, here also 4.7K is there. Okay, so this one is our S, right? So minus 1 minus S into 4.7K equal to 0, and S equal to 1 divided by 4.7K, which is equal to minus 0.212 milliampere per volt. So the answer is minus 0.212 milliampere per volt. Okay, because it is the value is delta IC divided by delta VBE, so that is why it is in milliampere per volt. Okay, and now let's do the next question. In the circuit shown in the figure, the silicon transistor used is operated in dash region. So we have to see if it is working in the cutoff region, in the saturation region, or in the active region. Okay, so if the transistor, the condition for the transistor to work in saturation, okay, we'll find out what is IB saturation. Okay, that is equal to, we'll consider this loop. After writing the loop equation, we'll get 3 minus IB into 10K minus VBE saturation equal to 0. From here we get IB is equal to 3 minus 0.8 divided by 10K, which is equal to 0.22 milliampere, and beta into IB saturation equal to 60 into 0.22 milliampere, which is equal to 13.2 milliampere. As you can see, beta IB saturation is greater than IC saturation. This means the transistor is in saturation. Okay, now let's do the next question. In the collector to base circuit shown in the figure, the value of the RC for BCC is equal to 15 volt, VCE equal to 5 volt, IC is equal to 5 milliampere, and HFE is equal to 100. HFE is simply our beta. Okay, HFE is equal to 100 and VBE is equal to 0.7 is. So we have to find out the value of RC. This one is 15. Okay. Now what we are going to do is we will just write the equations. So that will be 15 minus, this one is given that 5 milliampere, right? Minus 5 milliampere into RC minus 5. This one is VCE is given that it is 5 volt. Okay. Minus 5 equal to 0. That means RC equal to 10 into 10 cube divided by 5, which is equal to 2K. Okay, simple. That's all. Now let's do the next question. Okay, the transistor in the circuit of the figure is biased at a DC collector current of 0.5 milliampere. The voltage gain is, so we have to find out the voltage gain. So the voltage gain for this kind of a system is minus GM into RC parallel RL. So this is the voltage gain equation. So AV equal to minus GM is equal to I IC divided by VT. Okay. So that is equal to 0.5 milliampere divided by 25 milliampere into RC parallel RL. This one was 10. Okay. So that is 10 into 10 divided by 10 plus 10, which is equal to minus 100. Okay. Education. That will be, this one is positive and this one is negative. Okay. Minus 0.7. This is, let this be I. E. Okay. IE is being divided as 2 plus this BIX. Okay. So minus 0.7 minus IE minus 2 into 1K equal to 0. From here, after opening the bracket, we get minus 0.7 minus IE into 1K minus 2 into 1K equal to 0. Into 10 raised to minus 3, right? So, okay. So, that will be minus 0.7 minus IE into 1K minus 2 plus 2, okay, equal to 0, and IE equal to 1.3 milliampere, which is equal to our IC. So, this one is IC, and 6 equal to IC plus whatever is going here. Okay, let this be IY. So IY equal to 6 minus 1.3, which is equal to 4.67 milliampere. V0 equal to 1K into IY, which is equal to 4.7 into 10 raised to minus 3 into 10 cube, which is equal to 4.7 volt. Okay, so that is the answer. Now let's move on to the next question. The stabilization factor is, that is delta IC divided by ICO. Okay, that is ICO for the transistor amplifier circuit shown in the figure. So one thing to be noted is, for DC biasing, transformer acts as short circuit. Okay, please keep this in mind. For DC biasing, transformers act as short circuit. So the equivalent circuit will be look like this. Okay, so this will be the equivalent circuit. And now coming back to the question, I will write the equation over here. We will get 0.7 minus IERE minus, okay, this is plus, right? This one is great. So plus VEE equal to 0, and S is equal to, the general formula for S is equal to 1 plus beta divided by 1 minus delta IB divided by delta IC. Dou IB divided by dou IC. Okay. So what is IE? I'll write the equation here. We get 1.7 plus IERE minus VEE equal to 0. And what is IE? IE is equal to IC plus IB, right? IC plus IB, RE minus VEE equal to 0. 0.7 plus ICRE plus IBRE minus VAE equal to 0. And now differentiating with respect to IC, we will get 0 plus RE plus delta IB divided by delta IC into RE minus 0. So delta IB divided by delta IC equal to minus 1 and S equal to 1 plus beta divided by 1 minus of minus 1, which is equal to 1 plus beta divided by 1 plus beta, which is equal to 1. So that is the answer.